Hello, everyone. Thank you for coming to my talk today. This talk is going to be about a new PlugX fingerprint we discovered and called THOR. So who am I? My name is Mike Harbison. I am a senior principal researcher in Unit 42, which is part of Palo Alto Networks. I've been with the company a little over 4 years now. For those who can't recognize this computer on this slide, that is a Commodore 64, which happened to be the very first computer I received on my 12th birthday. And it's where I started my hacking research. And not to date myself, but this computer is 30 plus years old now. And yeah, so I've been out this for a little bit. And this is my cat. She'll be joining me during this talk. Her Twitter handle here, @myfatcatreese. And as you can see, she's daydreaming about some Windows kernel structures and programming or exploits. So to understand PlugX THOR and what we mean by PlugX THOR fingerprint, we first need to give a little background about what PlugX is. Well, PlugX, first of all, is malware, and it dates back to as early as 2008, so it's some 13 plus years now. It's a fully featured remote access tool. So your basic RAT, meaning that it can capture some of its capabilities are keyboard capture, keystrokes, upload, downloading files, capturing the user's desktop, starting files, pretty much your basic RAT. The infection methodology is typically delivered by a lure during a phishing campaign, basically to trick the user into opening or doing some action at which installs PlugX on the victim. It leverages applications associated with antivirus or other various security products, and I'll talk about that a little bit more in these slides going on forward. It uses custom encryption algorithm for its internal configuration data, its network comms, and strings within the binary. All PlugX since 2008, they use their own encryption, meaning they don't use standard encryption. In 2017, Unit 42 researchers, we discovered a different variant of PlugX named Paranoid PlugX. It has some different capabilities and features. It's very modular in design. And what I mean by that is you have your core PlugX, which runs on the victim or the target, and any new features are delivered via a plugin style loading. And those get loaded in memory without the core having to change. So the malware as it's running doesn't need a restart to enable these new features. So it's backwards compatible. To date, Palo Alto has tracked over 2,800 samples identified as PlugX, and it has been attributed to the Chinese cyber espionage group. So some of PlugX victims, one of the largest was in 2015. It was used against the United States Office of Personnel Management, otherwise known as OPM. For those who do not know what OPM is responsible for processing US citizens' security background clearances. So that data would be very valuable in the hands of an adversary, because then you have all the cleared individuals who have some type of security clearance doing classified work here in the United States. And to my understanding, some 21 million records were exfiltrated out of OPM's networks. And of those, roughly 19 million were of security cleared individuals. So again, very valuable in the hand of an adversary. It was discovered in the Vatican and used against some other Catholic Church related organizations. In 2014, there was an attack against Russian and Afghan and Tajik military diplomats. It exfiltrated almost 8 million records out of a Japanese travel agency, used against pharmaceutical organizations, video games, government entities across Southeast Asia. As you can see, they don't discriminate, but it still shows that PlugX is the go-to tool of choice once actors get on a box and they want to maintain some type of control over their targets. So, as I said previously, historically, PlugX uses a technique for code execution. That technique is known as DLL sideloading, basically abusing the trust of some application to gain code execution. And I'll explain that here. So you have your signed executable, which, think of Adobe or Microsoft, some application that's trusted by the operating system and other security products. and that application will start and it will load a DLL. But in this case, the DLL is the actor's DLL, and that DLL is nothing but an auxiliary DLL, which is responsible for loading the actor's code. So that your assigned executable starts, you loads your actor's DLL, and then your exe will call into the DLL via some export name. And that export name is where the code execution begins to start loading their PlugX payload. So here, in this case, that export entry is called, and it will then search for a file, and then it starts to decrypt and decompress that file. But at the same time, it starts a trusted Windows application. Now think of user init, SVC host, MSI exe. These again are trusted native Windows executables. And the DLL will start that executable, but it starts it in a suspended state, meaning that it's paused. And it waits for the decrypted and decompressed payload to be finished, at which time it will then copy or map it into the suspended process and then resume process. Now that process, think of SVC host, is running with the context of that payload in memory. So again, it's abusing that trust to gain code execution, and all PlugX rats historically use DLL sideloading for code execution. So what happened in March 2021? Something called proxy logon started wreaking havoc on the internet, and I'll explain give a little bit background about proxy logon. 4 critical zero-day vulnerabilities were impacting multiple versions of Exchange Server, and I'm talking about the perimeter Exchange Server, so 2016, 2019 versions of Exchange. A researcher that was working for DevCore, which is a Taiwanese security consulting organization named Orange Tsai, discovered this vulnerability. And here his tweet that he put out: just report a pre-auth RCE, remote code execution, chain to the vendor being Microsoft. This might be the most serious RCE I've ever reported, and it was. But at that time of reporting, Microsoft was tracking this vulnerability in the wild, and they noticed a Chinese advanced persistent threat, APT, that they called Hafnium, that was exploiting their Exchange servers in the wild, and they observed over 30,000 US organizations becoming compromised. At that time, this vulnerability, proxy logon, several other APTs jumped on the bandwagon and started leveraging this exploit for ransomware and other crypto mining campaigns. So it quickly became productized and started popping all Exchange servers out there. In the initial access, so you use proxy logon to exploit onto the box, and then you lay something down like a web shell. And that web shell is commonly referred to as China Chopper. And what that web shell does is it allows you further interaction with your Exchange server without any type of authentication, or maybe they have some authentication built in that only they can communicate with it or interact with it, and that runs at the level of system, so the highest privileges. So how did we come about PlugX-THOR? Well, we deployed a honeypot, an Exchange honeypot that was vulnerable to proxy logon, and we just waited to see who was going to attack it. And we started noticing that it was compromised, and we started looking at those log files, and those log files shed some activity, gave us some indication of what the actors were actually doing once they compromised our Exchange bots. And in this case here, I had the log. We noticed that a IP address of 101 was incoming, and that's based out of Hong Kong, was calling this shell.aspx, and that's their web shell. Remember, I said once they do compromise a box, they lay down their own web shell, and here it's shell.aspx. And there was a reference to Orange, and that's the one who initially discovered this POC. And here they're using WScript to run command.exe, passing it bits-admin. And for those who don't know, bits-admin is an executable that's on all Windows operating systems, I believe Windows 7 and up. And bits-admin, you think of your old FTP program, that allows you to download files to a host. And in here, they're using bitsadmin, and they're calling this GitHub repo, and they're downloading this file, arrow.dat. And so this is what sparked our interest, or piqued our interest. What is arrow.dat? So fortunately for us, that GitHub repo was still accessible and didn't require any type of credentials to access. So we downloaded arrow.dat, the same one that was referenced in shell.aspx. And, we started doing some of our initial analysis. First thing we do is, pull the file into our hex editor and say, what is it we're looking at? We're looking at a blob of data. We really don't know what this is, right? We're trying to discern, trying to make heads or tails of it. First thing that's running through my mind is it encrypted, compressed? And we noticed the first 678 bytes are these random characters, which I highlighted here. And following those bytes are random numerical numbers, or what appears to be random. So again, I'm thinking characters, numerical values. What is this? Is that some type of header, magic bytes? What is this file? But what stood out to me was this null byte right here. So following those numerical numbers with this null byte, and that null didn't exist anywhere else but here. So what is the significance of the null? I have nobody to ask, so I asked my cat, and she thinks it's a bird. Turns out the data is nothing but a header or garbage data. It's really not used. The significance of the null is basically a marker that can be dynamically used to determine where code execution should begin. And they do that, and it's pretty ingenious. They use this Windows API, lstir linked A, which reads byte by byte by byte up until a null. And that tells you how many bytes it has read, or the length of the string. So what they're using here is they're using lstir linked A to read in that many bytes, and then they skip one, and that's where their code execution begins. So think about some dynamic builder that's going to build your PlugX payload that could put an arbitrary value for its header and just doesn't really care how big it is. It could be 5,000 bytes. This Windows API is going to tell you where that offset exists. So I recreated how this process would work in some C code here. And basically you see using create file, and in this case, the payload for this PlugX sample is arrow.dat. So as I showed you earlier, the code execution flow, it's going to look for arrow.dat within the same directory as your DLL and exe, and it's going to get a file handed to it. It's going to determine how big the file is. It's going to allocate a buffer of read, write, execute, and then it's going to read that data into that buffer. And if you notice, highlighted in yellow here is that API call, lstir linked A, and then they create a function pointer and they increment it +1. So again, skipping all that data, and then that's where their code execution will begin. So the DLL will call into that payload at that file offset. So what is at that offset? Well, we can throw this into IDA, looking at that offset, and we see 770681EE. We recognize this as opcodes, so it's basic x86 assembly following that null byte. And this is where it starts to further unravel itself or decrypt itself. So this is valid x86 assembly. And as you can see, it's just basically jumping over and then starting its code execution. So what is arrow.dat? Again, I asked my cat and she says it's a bird. It's nothing more but a PlugX encrypted payload that gets loaded by the auxiliary DLL. And once decrypted and decompressed in memory, it's nothing more than your Windows DLL, your dynamic link library. And it is the core functionality of PlugX. So how did we identify this as PlugX? We just see this x86 assembly, nothing really jumped out at us. But when we started further doing deep dive analysis, we start seeing other artifacts that resemble PlugX. Remember, PlugX has been around for 13 plus years. I've looked at several variants of PlugX, so I just had a feeling maybe this is PlugX. And one thing that really definitively stood out to me, as I said earlier, is all PlugX use a custom crypto for decrypting their internal configuration data or strings. And in here to the left, you see the arrow.dat routine, and highlighted in yellow is the keys that this particular sample uses for decryption. And to the right is an older 2012, pretty much the same logic, shifting and addition, but different keys used. That and some other artifacts revealed that it was PlugX. As I said before, this is Thor. So historically, all of PlugX have this magic number 54C, 5447 in hex, which is plug into ASCII encoding. But it turns out this sample had 54, 48, 84. As you can see, the word Thor in ASCII encoding. So the decrypted arrow.dat here is checking for Thor, and to your right, that same variant is checking for the word plug. And this is the first time I've come across a PlugX sample that is actually using Thor versus plug. So what is this actually decrypt to? As I said, all PlugX malware families have some type of internal configuration, and this particular one, once decrypted, has a command and control server. It's C2 that it's going to communicate out with, rainydaysweb.com. It will attempt to communicate with that domain on 80, 443, 53, or 8000. It will alternate between protocols, either TCP or UDP. It hijacks, like I said, it abuses trusted Windows, trusted applications. In this case, it's disguising itself as HP digital image. And as you can see, its persistence technique is installing as a Windows service. And here it's arrow.exe. So that's your signed executable that's going to run. It's going to look for its corresponding DLL. In this case, it's going to be the actor's DLL, which is then going to look for its PlugX payload, arrow.dat, and that's how it gains code execution. So every time the machine restarts, it's going to kick off this arrow.exe and start those chain of events. It's also configured to use Google's DNS server. And historically, all PlugX samples have some type of associated campaign ID. And this one just happened to be 1234. So why the change? The best we could do is surmise as to why the change, because we really don't know. I'm just speculating here, maybe to evade detections, because it's been around for 13 plus years and everybody knows that plug is a signature to look for. When it gets loaded in memory, if you're scanning memory and you look for any of the contents having plug, you know you have PlugX running on your box. So Thor may evade it. Possible some new builder out there that's building these payloads that's just putting Thor there. The earliest variant that I could find in my hunting goes back to 2019, and I'm showing here how this module would look running within the process of userinit.exe. Again, a trusted Windows valid executable, and as you can see here, it has Thor, but it's backwards. And I should state that it removes the MZ header, and you would have this Thor here running within userinit. So it's time for some tool development. My cat's awake. She's ready to develop some tool capability for this. So we started studying the PlugX payloads themselves. We really didn't care too much about the actor's DLL, because those are always pretty much unique, because they had to be built for the associated EXE. So I really focused my effort on the PlugX payloads themselves. Remember, you have that random data, that numerical number, and then some null byte. And as I was looking for those and doing my hunting, I came across some other PlugX payloads that followed that format. And I found one here that has 10 bytes and then a null. Well, it turns out that those first 10 bytes are the XOR key, the XOR key, that are used to decrypt the payload. So anything really following a null kind of stood out to me. So yeah, so I built a tool that can then decrypt the two types of payloads that I discovered that I talked about. So it attempts to identify the PlugX file or the encryption, and then it will generate two files. It will output a c2info.dat, and that's the one that has like your basic internal configuration data, such as your command and control, the ports, the campaign ID, and then your module.dat. And that file, the module.dat, is the one that you can load into IDA Pro or Gita or whatever you like to do further a static or dynamic analysis of how this is going to run within your, or submit it to some sandbox. This is the module that gets loaded in memory. So how can we detect this in wild? So again, I turned to my cat, and this time, surprise, she's awake. She doesn't say a bird. She says we can just create a Yara signature based on the 103 bytes of opcode used to unpack the arrow.dat. So what's unique is not so much how the DLL is, but the decryption routine within the PlugX itself. Those bytes are pretty much a constant, so we can signature off of that, and then we can go look for other PlugX payloads that might exist. So I created those Yara signatures, deployed them in our favorite tool of choice, our favorite environment, that being VirusTotal, and then we had a hit. And as you can see, it's pretty recent, July 14, 2021. This PlugX sample was uploaded, pdvdlib.dat. And as you can see here, 0 of the 58 engines detected it as malicious. Understandably, because it's just a blob of data, and without the associated other chain of files to execute it, VirusTotal doesn't really know what to do with it. None of the security vendors are like, meh, but we understand what it is. So what we can do, we could download the sample, and we created another tool. We, being Unit 42, created another tool, and coincidentally, we're fans of Marvel and Avengers as well. And what does Thor always have? Thor has his hammer, or also known as Mjolnir. So we created a tool called Mjolnir, and it is basically a configuration extraction tool. It was built for Cobalt Strike. Cobalt Strike, similar to PlugX, it has an embedded configuration file that's encrypted as well. So we built it to decrypt Cobalt Strike. So we modified Mjolnir to handle PlugX as well. So now it will extrapolate the data within a PlugX sample, that configuration data, and it will also, within Palo Alto Networks systems, update any verdicts. So without having the associated actors DLL to load this in our sandbox or any sandbox, we now know what the C2 server is. We now know what the ports are, so we can automatically update verdicts. But it also gives researchers the ability to search on those, or pivot search, or just do some threat intel search on those domains. Again, the advantage of this, it does not require any of those other associated files to run. And this is what it would look like in our system, Mjolnir. You have your C2, as I mentioned before, rainy days web. Your config file name here is Adobe Update. Again, it's abusing that trusted application. So for this particular sample, it came through as an Adobe Update.dat, which means it would have an exe and DLL, some type of association with Adobe. And then you have your config path here where it would be extracted to. Hijacked application name, in this case, AAM. I'm not really sure what that is. And then you have some basic artifacts of the sample itself, so you can do some other searching on. And as my cat is again sleeping, but she would say that's pretty much winning. And if you would like to read up further on, about this PlugX Thor sample, I have a blog here that I listed that goes further in detail, a little bit deeper into the technical aspects of it. I did release this tool that I talked about earlier. It's a simple Python script that you can use to decrypt 2 of these payloads, PlugX payloads. So if you come across them within your network or in VirusTotal or wherever, you can just send it to it and it will output the corresponding C2 information. I welcome any and all feedback, questions, or problems in my email address here. Please feel free to email me at any time. And, that's it. I hope you enjoyed my talk. Thank you for coming and enjoy the rest of the con.